This is Rob Gray from ASU and PerceptionAction.com. Today on the Perception in Action podcast, my interview with Andrew Wilson, Senior Lecturer in the School of Social Sciences at Leeds Beckett University in the UK. Hi everyone, welcome to the Perception in Action podcast, where I discuss how psychological research can be applied to improving performance, accelerating skill acquisition, and designing technologies. In today's episode, my interview with Andrew Wilson from Leeds Beckett. Andrew received his PhD in psychology and cognitive science from Indiana University. Along with doing lots of great research, he is one of the most active and passionate advocates of the ecological approach to perception and action. He and Sabrina Golonka share lots of great information on Twitter, @PsychScientists, and on their blog, Notes from Two Scientific Psychologists. In the interview, we discuss ecological psychology ideas like motor abundance, functional equivalence, and degeneracy, Andrew's recent study on task dynamics and information in throwing, his work on affordances and throwing of prehistoric rocks, and the current and future state of the ecological approach. I'll apologize up front, I got my money's worth from Skype in this interview, and so the audio is a bit choppy in places. I hope you enjoy.
Not 10 years ago, I was a child. I was a good boy and you let me go. Now I'm on a talk show. So
today my guest is Andrew Wilson, Senior Lecturer in the School of Social Sciences at Leeds Beckett University in the UK. Thanks for joining me today, Andrew.
Hey, thanks for having me. I'm a big fan of the podcast. It's been great.
Oh, thank you. Now, I wanted to have you on for a couple of reasons. The first, you have done a lot of really interesting stuff on throwing and catching research we'll get to later. But the other reason is you are kind of a very passionate and outspoken advocate of the ecological approach, which I know a lot of listeners to this podcast and a lot of people working in sports and are really interested in. So with regards to this latter, I wanted to ask you, can you tell us a bit about your background and maybe how you became such a strong believer in this approach?
Yeah, sure. So, I started out, I'm from New Zealand originally, and I did my undergrad at the University of Otago. I did psychology there. And then I just kind of followed a few interesting opportunities, actually. So I had the chance to go overseas to the States to finish off my undergraduate. And it was when I was there, I kind of discovered cognitive science as a thing, as sort of a topic that you could study. And also the idea of going on grad school and doing a PhD. I was like, I'd never thought of that. And so after that, I took a year out, went to work in a pub in London, the way you do when you're from New Zealand. And I found Indiana University, which just was a program that really sort of gelled with a lot of my sort of interests at the time. I originally went there to study with Linda Smith and do categorization stuff in infants and babies and things. For a little while, I met the person who became my advisor, Jeff Bingham, and I was gay actually for one of his classes. He was teaching this history and systems class. And, he teaches it beginning Greeks and capping everything off with James Gibson as like the pinnacle. So it was a fun class and we just started talking. I was like, well, who's James Gibson guy? And I started talking, and then I was a TA for his perception action undergraduate class the next semester, and that gave me a bit of a background on some of the material, and we just got chatting about it. And then I said, can I come play in your lab? And he's like, sure. And so I switched over into his lab, and basically I just blamed Jeff entirely for my interest in the ecological approach. Really enthusiastic, really passionate. He's a really amazing scientist. He's been doing this stuff for years. He's been getting into all the big questions and has sort of firm opinions and quite often back those up on, a whole raft of stuff. And we just got into it and it was great. So, and then Indiana was just a fun environment intellectually as people from all over the place doing different kinds of aspects of cognitive science. And we'd often get together in reading groups and socially and all sort of stuff. So I think I was ready to be converted. I think it was like I felt pretty good about it. As soon as I started hearing about it, it started to make a lot more sense than a lot of the traditional cognitive stuff that I'd been studying. I was like, oh, actually, you could do something with this. You could build a robot with this. You could actually kind of like, we're talking about real bits, talking about information. It's a real thing. It's not just abstract representation that may or may not be there. And so there, I got into it. It was interesting. Started working on coordinated rhythmic movement. And started getting into the information things there and learning how to do it. It's hard, but it's very satisfying because when it works, right? You don't just get a little nudge. If you hand information, boom, you're done. You're off. That was my starting point, was working with Jeff. And then I came over to the UK as a postdoc with a friend of Jeff's, Mark Williams, when he was up in Aberdeen. And we did some stuff up there. And then I came down Warwick for a year and did a postdoc there, and took my first job at sports science, actually at the University of Leeds, and then back to psychology at Leeds Beckett. So I've just been following jobs and interests for a little while now. But yeah, sort of all through it, I've just become really interested in kind of pushing the ecological approach a bit, just trying to make it really look as much as possible. Because it seems like a really good way of doing some things, and there's a lot of problems still to be solved and a lot of things we have tackled. And I think we're kind of in a position now where we can get up to some of it. So my big goal has just been to push that. I can't just go off to a room and sort of think about it. So I like talking to people and banging ideas around. When Sabrina and I started doing the blog and started doing Twitter, getting the ideas out and talking to people has been really useful. So yeah, that's how that kicked off.
Yeah. No, I agree. I think people that don't know the area well, I don't know if they realize that first, it's not been around for a very long time relative to all the other theories. And there's still a lot, it's still very malleable, right? Some people think it's just kind of there's a Bible, Gibson, and then there's no more to do. It's just applying it. But I think you've done a good job at trying to, we need to get more details about these things and clear on these issues. Okay, so maybe digging a bit deeper, can you, what does the term ecological approach or ecological psychology mean to you? Kind of what's the key difference?
It's quite a big mindset shift from the more standard cognitive representational information processing kind of approaches. For me, I think it boils down to the place where you start finding differences, the place where you begin is in perception, and you start taking perception really seriously. And that was what Gibson actually did. Like, he started doing other things, but then as he got into it, he just realized that there were unanswered questions about how perception worked that was going to have consequences all the way up through the system. And so he just got really interested in trying to figure out that. And for me, I think the big thing that in ecological approach is always, what is the perceptual information that's available in a task that can support the behavior that you're trying to explain? And if you can come up with a story where you can identify that information and then manipulate it and show that the behavior changes with it, then you're off to the races. And so that's hard work. The hypothesis is that most of our behavior is not pre-planned or sort of abstract and anything like that, but it's embodied and embedded in the environment, and the shape of behavior is connected to the way we perceptually interact with our environments. That means you need to know two things. You need to know what it is about the environment you're perceiving, because not everything's relevant. And then you need to know, well, how do you go about perceiving those properties? And then you get affordances as one of the things that you're mostly perceiving. And then you get perceptual information, specifying information variables as the way that you get access to those affordances. So for me, the ecological approach, the trick is to take very seriously that behavior is being shaped in real time by perceptual contact with the environment.
Yeah, no, I think that's a good way of thinking about it. I know a phrase I often see used is task dynamics create information.
Yeah.
You already kind of touched on that, but can you tell us a bit what you mean by that?
Well, yeah, right. So if you're going to tell a story in which the environment and your perception of the environment is shaping behavior, then the first thing you need to do is you need to have a theory of what it is in the environment that is action relevant. What is it that we're actually interacting with? Because not everything matters, right? There's a bunch of ways, people do crazy physics to try and figure out how things are built, but most of that's not relevant to an organism because we're too big to worry about electrons and all that sort of stuff. So the question is, well, what's a good way of describing the animal-sized environment, and is there a way of doing that in which things like affordances make any kind of sense? And so the throwing work that I do and work that other people do as well, I've tried to formalize that and say, right, okay, if we're going to characterize the environment in a useful kind of way, we're going to have to do it at the level of dynamics. That's the tools that we're going to have to use in order to be able to have a complete description of the ecological environment. And so what that means is, if you want to describe a task, you use dynamics. Dynamics is just a mathematical framework, right? Dynamical systems theory. But dynamics is a mathematical framework that contains some things and not others, right? So it lets you talk about position and changes in position, so velocity and acceleration. So it lets you talk about change over time, but it also gives you variables like mass, which lets you talk about the forces that cause those changes. And that's what you've got access to in a dynamical description of something. And it turns out that if you want to adequately describe the physical environment of an animal-sized organism, those are the tools that you need, right? You have to start there. And so characterizing the environment is about doing it in dynamical terms. And then doing it ecologically means not just describing it any old way, but trying to use those tools to build a description of the environment as it's presented to an organism. And that's where you get into affordances, the idea that you don't just perceive that something is a certain number of centimeters away, but that it's within reaching distance, for example. The basic idea of task dynamics is that you describe one task at a time at a dynamical level of analysis, and that gives you the right description of what it is that the organism is trying to do, and that's your starting point for explaining their behavior in response to that task.
So you mentioned in there your recent throwing paper that is come out or soon to come out in JEP.
Should be
is it out? Yeah, I can never know.
I know it took a little while, but it's on the blog anyway. So.
Okay, great. Can you tell us a little bit about what you did in that study and what you found?
Yeah, sure. So it's funny, actually, relative to a lot of your guests, I'm not a particularly applied researcher. And actually, even though I'm doing throwing and have some interest in sort of applying some of this, it's like this particular research is very much, it's not particularly sort of applied, but it's an extension of actually, of stuff that Jeff has been doing for years on looking at the task dynamics of maximum distance throwing. That's what Jeff and one of his former PhD students, Arthur Zhu, have been working on for a number of years, and that was Arthur's PhD. Was it figuring that out. And then when I was at Sports Sciences up at Leeds, I had access to some of the technology and some students who were interested in working on this kind of topic, and I wanted to get into it anyway because it was kind of cool. And so we started talking about doing the task dynamics of targeted throwing, and that's the JEP paper. So it ended up being quite a large study, but we ended up making it, it makes a number of points. So the basic setup was this. I was at Leeds and I had access to some fairly expert local cricketers. So I'm in Yorkshire, and that means you've got quite a few good cricketers floating around. So they weren't Yorkshire Cricket Club, but they'd all been playing at club level for quite a long time. And then Arthur's in Wyoming, and he's got college level baseballers, male baseballers and female softballers. Arthur and I got these targets built, these large 4x4 foot perspex screens that are mounted in this big frame, and you can place them sort of anywhere you like, and then you can rotate the frame so that you can turn it from vertical to a horizontal orientation. And so that was the target, marked out in masking tape, a big target in the center of that. And then we got these expert throwers to throw tennis balls to hit that target, and then we varied a bunch of things about the target. So we varied the distance. So the target was either 5, 10, or 15 meters away, and we varied the height of the target. So we set the center of it to be at 1 meter, 1.5 meters, and 2 meters, which is roughly eye height plus or minus half a meter. And that was just kind of an initial kind of manipulation to see if sort of eye height kind of things matter. That's a parameter that comes up a lot when you're looking at sort of space perception and how you perceive distances out to those kinds of distances. So we did that just as sort of an initial manipulation of that. And then we just got people to throw a bunch of throws to each of those target locations, and we measured them, right? So we tracked them with high-speed cameras, and we measured the release velocity, the release angle, and the release height they produced in order to hit the target, and then we counted how often they hit the target, etc. And so that was the first part, was just this empirical part. And the first thing we found was that, man, expert throwers really are good at this. It's kind of a joy to behold. These people were just whizzing these tennis balls in from, 15 meters away without sort of any effort. And it was just hitting very close to the center. So first, we got a lot of good data out of them. And that's, as a first swing, you need people who are good at the task. We're going to get into learning later on. So the first thing was that they were all good. They all produced mostly hits. There were very, very few misses. But then we started looking in more detail at exactly how the release parameters varied as a function of these task properties, these target properties, to see which ones mattered. So the question is, okay, if I change the distance, if you're throwing to a vertical target, you could actually just throw as hard as you can and slam it into the target. And it doesn't matter how far away it is. You could just throw at full speed and never have to change anything up, and that would be perfectly fine. That's one sort of option. You'd never have to change anything. Mm-hmm. You'd never have to do any of that sort of work. You could always just whiz it in as fast as you can. And the first thing we found was that throwers don't do that. They scale their velocity perfectly, really nicely to the distance. So basically, as the distance increases, they throw faster so that they cross that distance. But it was really nice, even across all the groups. It's sort of independent of exactly how far they got. Everybody did this. So basically, the first thing is that that's showing us that they are clearly perceiving the target, and they're scaling their behavior in response to that perceived distance. So that's the first thing, is that we now know that target distance matters to the affordance of this thing to be hit, because it's affecting behavior. And the next thing we did was we varied the height. Come out of that was that release velocity didn't change with that, but people changed their release angles. So as it went up, the release angles went up. Basically, these experts, they like to throw a rope. They like to throw it fast and they like to throw it flat, with the idea being that's all they're training. They're trying to minimize the amount of time the ball spends in the air, right? So if you're trying to for a run out or you're trying to get it in to get someone out at a base, you got to get it in to cover that distance as fast as possible. Do that by throwing, instead of a nice big loopy throw, you throw it fast and flat. So to the vertical target, that's what they did. They scaled their throws. And so it was nice, sort of beautiful data. So clearly they're perceiving the target location and it's affecting their behavior. So those are things we're going to have to worry about now when we can get to the affordance. And then the second thing we did empirically was we tilted the target. So instead of making it vertical, we simply tilted it so that the target was horizontal and lying flat. And we did that after we found that they preferred to throw fast and flat. And we forced them to throw the big high loopy throw that can also cover that distance. So get out of that comfort zone. And the thing is, does that affect their performance, right? Are they good at that other one because they've practiced it a lot, or are they good at it because they're perceiving something about the current environment? And so we gave them something that they won't have practiced anywhere near as often to try and loop it in and hit this target. The first thing we found was that they were very accurate again with very little sort of come up or anything. There was almost no misses. And the second thing is they all just perfectly moved and shifted the kind of release parameters that they were producing to suit this new target. And they were just producing these nice, high, slow throws that were just landing on target and kind of nailing it almost, 9 times out of 10. So the throwers, we had this nice data from the throwers, and now the question was, could we figure out why they were picking the particular parameters that they were? Why were they producing the particular releases that they were, other than to hit it? Was there any kind of reason, anything that was structuring sort of anything interesting in their behavior? So that's where the simulations kicked in. So this is where the whole second half of the paper kicks in. I had a friend of mine up at the University of Leeds, an engineer, Andy Waitman, who wrote some simulations for us, where basically he would simulate a throw across a certain distance to try and hit our target, and he would vary the release parameters all over the place systematically. And then he'd just figure out whether or not that combination produced a hit or a miss. Mm-hmm. And then we just mapped out which combinations produced hits and which combinations produced misses. And then in the paper, there's a whole bunch of graphs. And what you get are these kind of U-shaped curves for the vertical target, where there's a big thick region on the left where there's sort of a big cluster of release parameter combinations that produce hits. And and they're all very low release angle, high release velocity. And as the release angle increases, you can still get a hit onto a vertical target, but it gets harder and harder and harder and harder and harder. And what happens with the horizontal orientation is that shape changes, and suddenly that thick region is no longer up on the left, but it's now down the bottom with higher release angles and lower release velocities. And basically what we found was if you stick the human data on top of these, then the human data is organized effectively with respect to that stability. So people like to throw in a region of the parameter space that has some tolerance for error. They like to throw in the thickest sort of region of the space. And what that is it means if they get it wrong just slightly, then they're still going to hit. So even if they don't get the release velocity they're kind of aiming for, they're still basically produce a hit because there's wiggle room there, and they don't live in the more difficult regions. And as that region of the parameter space moves, their performance moves nicely. What we're saying is that that big U-shaped curve is a mathematical description of the affordance of that thing to be hit, and we're arguing that the people, their throwers, are perceiving that affordance and using it to organize their behavior. That's what's driving them to throw in the particular ways that they throw. So that's that paper. That's the first sort of big swing at doing the targeted stuff, trying to get a handle on the dynamics of that and how that organizes behavior.
Yeah, I think that's really nice. I really like that they kind of people naturally pick up this area where the most tolerance of variability, a little bit of error here and there is going to be okay. I know some people, I'm particularly thinking like kind of the hitting movements studies of people like Ellie Brenner, that talk about the reason we do things fast. Did you find any evidence of that? People want to throw faster to try to, I think it reduces noise, which is probably not something you put in your model, but are there any other constraints, trying to conserve energy, trying to reduce those kind of things?
Well, first of all, so one thing out of this was we had the 3 sporting groups, right? We had the baseballers and the softballers and the cricketers. And the baseballers were all male, and they all throwed. They were all throwed in the region of a 90-mile-an-hour fastball. They were all whizzing it in, and then getting a bit slower as the target got closer. And then the female softballers were throwing a little bit more slowly than that, but they were much more tightly clustered and sort of more more reliable over trials. And then the cricketers were much slower, actually, and that replicates some earlier work, it turns out. So it seems to be the case that people were happily operating sort of quite close to their preferred top speed. So they were whizzing it in fairly quickly. But even within that, they were still responding to the changes in target distance, for example. So they weren't just trying to get it there as fast as possible. They were trying to get it there as fast as possible, but the target was closer. They weren't throwing it as fast. And obviously generating big release velocities it's hard work. It's complicated. So yeah, I guess they were kind of responding to the fact that they wanted to get it there quickly, but they didn't need to expend as much effort to cross 5 meters as they did 15 meters, so they didn't. Mm-hmm. And yeah, so I mean, at one level, you do see a little bit of that.
I think this, I know you mentioned you're going on to do learning next. I think that's going to be really interesting because it's kind of a two-sided coin, right? On the one hand, it's really nice that we're so able to pick up these task parameters and tune into them and adjust. But at the same time, that can be dangerous if we don't give people enough variation in the learning phase, right? They're going to latch on to this one strategy or one, control way to control. Yeah. Yeah.
Well, that was interesting. Why we ran the horizontal target conditioning, and we've got some ideas for running this a little bit more gradually, where we vary the orientation sort of more gradually. The way we're sort of thinking about that is that the vertical target affordance and the horizontal affordance are slightly different shapes, but we're considering them as sort of, it's like a continuous transformation of the same affordance, right? It's not two different things. It's just a different kind of slightly different version of the same thing. That's why we ran the horizontal target was, okay, we know these people like to throw fast and flat. Their preferred thing, that's the thing that they really do practice over and over again. That's the mode that they're in all the time on the sports field because of the demands of the game. What happens if you bounce them into something that they do very often? Does their accuracy suffer? Are they any good at it? Can they do the touch? Does it make any sense? Or have they just learned that one thing? And the cool thing about the horizontal orientation data is it shows, no, actually, they and we were mixing this up across the experiment. People just switched into throwing quite happily to the horizontal target. They just changed the kind of throw that they produced. Their accuracy did not suffer. They were still throwing with ridiculous precision, actually. It was kind of amazing. So the argument there is that people aren't just executing a throw that they know how to do. That this within group comparison of the two different target conditions shows that they're actually sensitive to the current task demands and are using that to shape their behavior. And that's what's fun about throwing is that, it's actually, I don't have to do too much to constrain them in order to make this something I can actually study, right? I don't have to lock it down too much in order to make it rigorous, which is kind of nice. And then the maths is relatively tractable as well.
Yeah, I've had the same in baseball. You get projectile motion. It's a nicer thing to study, yeah.
So it makes the mathematics, the dynamics analysis, it makes it tractable. The science, I can just get these people to come in and throw without kind of forcing them to sit in a chair and do something weird. So that's kind of nice. And it just means that you can actually get a bit of a handle on this.
So turning to your other recent study, you're looking at affordances in rock throwing. In prehistoric rock throwing. And so a couple questions there. You've mentioned affordance a couple times. Can you tell us what that term means to you? As I said, it's still kind of being defined, I think. And then maybe tell us about that study you did.
Yeah, so one of my goals here is to get the ecological approach to just kind of get a bit serious about a few of its key terms and just sit down for a little bit on the thing that's actually going to work. And affordances is one of those terms. People talk about it as an opportunity for action and all that kind of stuff, but that's quite vague. You could have all kinds of opportunities for behavior. And then the question is, well, how do you perceive them? That's actually important. They have to create information. Otherwise, who cares, right? So there's kind of a big sort of in the theory of ecological psychology, there's two notions of affordance. One is the affordance as a relation. So it's a thing that is defined simultaneously by the organism and the environment, thing out in the environment. And that's one way of thinking about it. And that tries to capture the idea that you can have a chair that affords sitting on for me, and I can create the affordance, but a child, for example, would come along and it might be too big for them. And so the affordance isn't present for them. That's kind of trying to catch that idea. But it falls apart a little bit because it immediately, we made this argument in a throwing paper, it just immediately becomes really hard to, it's being created by the interaction between the person and the environment. And it's hard. Like, how is it created? What is it that light is bouncing on, for example? And also, how do you learn it, right? If it doesn't exist until you know how to do it, then how do you make it? How do you get in on that? So for me, the point of all the throwing work is continued empirical demonstrations of the best way to go about affordances is to think of them as properties of the environment, dispositions of the environment. And so a disposition is something like position of salt to dissolve in water. So if you've got some salt and it's just there and it's not dissolving, but if you stick it in some water, it'll dissolve because it has the position, it is disposed to do so. Same with an affordance. It's a product out there and you find it with no reference in the organism and it's just there and it's interacting with light and it's doing its thing and it's creating information. Then if an organism comes along that happens to have some matching properties, some complementary properties, like, for example, I come across my chair and my knee comes out to about the size and I can bend in the right places, then I can now interact with that affordance and I can effect it and I can enter into a little perception action loop that means that the affordance can then shape my behavior. So for me, an affordance is a thing, it's a property that's out in the environment and it's a way of describing the physical environment in ecological terms is what it is. It gets back to that idea of you have to have a good theory of what the environment is as far as an organism goes. And that's an affordance is a thing that's an ecologically relevant, perception action relevant property of the world. There's lots of other properties of the world and some of them just don't matter. For me, that's what an affordance is. So it's a thing you can identify. And so all the work on the target, for example, and defining the affordance, we did it all with respect to projectile motion and we had no conversation about the details of how the thrower interacted with it. And we came out with what I'm hoping is a fairly useful analysis. And so this new project with stones was the same basic idea. I had some information about these objects and it was about figuring out whether or not those properties of those objects, independent of who was interacting with them, the question was, do those properties make them good projectiles? And so the cool thing about these objects was that they were these prehistoric rocks from South Africa. They're 500,000 years old. So that was fun. So yeah, so this project, this was simply the most good old-fashioned science fun I've had in I don't know how long. I took a talk about the throwing paper data to Liverpool, got invited to give a talk out there, and I mentioned in the abstract, throwing's been involved in our prehistoric success, and that's all kind of cool. And that caught the eye of a couple of archaeologists at Liverpool who came along to the talk. And they were asking me all these questions about the analysis, and it basically boiled down at the end. I was like, if I gave you some information about some prehistoric rocks, could you do that thing you just did in the talk and tell me something useful? And I was like, probably, yes. And so we stayed in touch over email for a little while and we kind of batted around some ideas and then we latched onto these set of objects called spheroids, and they're rocks about the size of a cricket ball, and they're fairly solid rocks, and they show up in a bunch of places. They've been around for a long time, but there was this particular set that got dug out of this place called the Cave of Hearths in South Africa. That was the set we ended up sort of focusing in on. And so what we did was Larry Barham, one of my colleagues, sent me data on the sizes and the weights of these rocks, and that was my starting point of these projectiles. And then basically I sat at my desk and opened up MATLAB and started doing some simulations. And what I did was I took that data about the rocks and I pumped it into a simulation of projectile motion, and I figured out, okay, what would it take to throw at certain distances, etc. And then I went and looked at some of the old data from Jeff and Arthur's work on maximum distance throwing, and they had a lot of data about how to figure out release velocity given the weight of an object. So they'd identified a relationship there in their data, and they'd figured that out. So I was able to use that. So I had the weights, and I was like, okay, well, now I can get the release velocities. And then I figured out, given that release velocity, what's the maximum distance you could throw it? And I figured out the angle you could throw it at that. And then we made an educated guess about the release height based on some skeletons that got found in the area that were dated to about the same size. Then I had a set of projectile motion simulations that were about not just any old projectile motion, but they told me how those things would move if they were thrown by a human. And then it was like, well, okay, looks like they're going to travel a long distance. They'd go up to sort of 25 meters or so, and that seemed quite useful. Then the question was, okay, if you hit something with one of these, like if you hit a deer, what would you do to it? And so I went digging around the literature, and I came across this sort of forensics literature where people had been developing mathematical models of what happens when blunt instruments hit things, hit tissue and animals and people. And, people use these models when they're doing sort of forensics reconstructions of crimes and things, is to try and figure out how much force was used to figure out what kind of weapon, etc. So there's this slightly creepy, weird literature on all of this stuff. But what they do is they come up with these mathematical models so that you don't have to do any more sort of weird stuff with animals, and you can just pump it all in. And so I came up with this number that gave me a measure of how much damage an impact would do. So then I've now got all the numbers, and then I took all these objects and figured out how much damage they'd do to a fairly big animal if they got hit at various distances. And basically what we found was that almost like 88% of the objects in our set, if they were thrown by a skilled human and if they hit the target, they'd be hard enough, they'd be going fast enough to break a bone, to do some fairly substantial damage to a fairly large animal. And then you think, well, okay, that doesn't seem like you can't kill an animal like this with one shot. But it's like, well, okay, what happens if you're hunting with a pack of friends, right? Which is something we know people do. So all of a sudden you all stand up and throw the rock. You get hit with 6 of these. Suddenly you're in big trouble. And then even if you just break a bone, that's going to slow the animal up. And then you can go off and you can persistence hunt it for a while and just chase it down. And the more injury you do to it, the easier it's going to be to hunt down. So we don't know for sure that these things were thrown, but we have shown, based on these simulations, that if you did throw them, they would be brilliant weapons. And they're cheap and they're easy, and they came from a river down the road, and they just get made. They weren't made by anybody. They're just naturally eroding shapes that come out pretty spherical because of the way the rock erodes. So the argument is just, okay, we take this affordance analysis, and the whole thing is premised on what are the properties of the objects and how do they relate to the task of throwing for damage. And then we find out they're perfectly suitable for that. And then we can make some inferences about the behavior, about the prehistoric behavior of some humans, because we know that humans have been throwing for millions of years, so it's well within their range. So that's the argument there.
That's a really cool story behind that paper. You had to go way outside your comfort zone, it sounded like, digging up things, like old school scientists, right, doing all these different topics at the same time. That's great.
It was so much fun. It was just one of those projects that like you'd never be able to sell a grant committee initially. You know, like now that I've got the paper out, I'm going to try and sell a grant committee. I'm doing some more. But for the first one, it'd be like, no, that makes no sense. But it was so much fun, and it worked so well. Like, I was blown away. I was just able to reconstruct all the numbers I needed from half a dozen different places in the literature, and with some helpful advice from a bunch of people sort of around when I just sort of asked them questions and things. And then it came out. I was like, oh, this is so cool.
So next I thought we'd do something a bit different and try a bit of rapid fire here. So
sure.
I have a lot of, I think a lot of people listening are interested in ecological approach, and there's a lot of terminology that gets thrown around. So I know you read a lot in this area and you write a lot about it in your blog. It's Notes from 2 Scientific Psychologists, which I'd highly recommend. You're very active on there. So I thought I'd throw out a few terms and you could give us like a quick explanation or what comes to mind for you. So you ready?
Yeah, sure.
Okay, so first, functional equivalence.
Functional equivalence. So the idea there is that there's a bunch of different ways of doing most kinds of behaviors, I guess would be the way to go at that. So if you want to be able to just, take a simple example, you're reaching out for your coffee cup. There's actually a bunch of different ways you can do it. So most people just reach out in a straight line and you can just do it. But if something's in your way, you can reach around it. If your arm is tired, you can go more slowly. So there's a bunch of these things that can pull off. And the idea is that they're all equivalent because they pull off the same function, namely moving your hand to grasp the object. And this gets into the whole degrees of freedom versus what's Latash's phrase, the bliss of motor abundance, which I love. Mm-hmm. It's just the idea that having this kind of having these options, having the ability to be able to respond to the environment in a bunch of different ways, it's a source of flexibility. It's not a problem. I mean, it comes with some issues, but it's not fundamentally a problem. It's a huge perk. It's a massive benefit of the system, which enables you to cope with what's going on in the environment.
Yeah, and that was kind of my next one, motor abundance. It's kind of the same. I noticed you have a great video of, is it a lynx or something at a zoo? Trying to get down from a rock. It's like a leopard or a tiger or something. I can't remember. Or a snow leopard. That's right. Yeah, it takes the most unpredictable action to get down off this thing.
I know. I couldn't stop watching it, but then I started thinking. I was like, okay, let's start on the assumption that animal is not insane, and try and figure out why in God's name it might have done that. And I have no idea if my analysis is true, but the idea was just, what would make you do that? Mm-hmm. And it basically boiled down to, it could do it. And right there in the moment, it was the best solution.
It made sense to it for some reason.
For some reason. But that's it. And so if you don't, but in order to understand that, you have to kind of, I had to think about the environment that it was in. What were the affordances? What were the opportunities currently facing that animal that it could do, that it couldn't do? What was it trying to achieve? So I had to make some guesses, but the idea was all just about trying to figure out what was the kind of the ecological shape of the environment that it's in that made that maneuver a legitimate option. And it clearly was a legitimate option because it pulled it off without blinking. So
yeah, it worked really well. Yeah. Next one, invariant.
Oh yeah, this one gets messed up a lot. So when I was a PhD student, one of the lessons that Jeff really banged into my head is that there's the world and there is information about the world, and those two things are not the same thing. You have to keep them separate in your analysis. And one of the things I see about the word invariant is it gets thrown around as if it was describing something out in the world a lot. So people talk about invariant configurations between, rugby players as they try and do a particular move, or an invariant configuration of in some sport or whatever. Right, you can use the word in that sense if you want to, but you're not using it in an ecological sense. Ecologically, an invariant is an information thing. And an invariant it's a stable feature of, take the optic array, right? The light the light coming into my eyes, each sort of, and it's bouncing off my coffee cup, sort of the specific example, the specific little bits of light coming off there are changing intensity as I move and as I get closer to it, etc. So there's a lot of wild variation going on in terms of just the local behavior of the light. But then there's these, what's referred to as a higher order relations. There's things that are remaining true across those transformations. So as I get closer, some of the details are changing, but the relations between angles on the object, etc. All of those are even though the absolute values are changing, the relationship between them is staying the same. And Gibson's argument is that, first of all, if you're going to look for information, it has to be something that persists, that is sufficiently stable that you could potentially learn to use it, because learning takes time. And then he looked and identified that you could have these invariant features of, for example, the optic array. And then if you look at those, it turns out that those are the kinds of things, those slightly more complicated things are the kinds of things that can be informative about interesting properties of the environment. So if you put all that together, what you've got is that ecologically, an invariant is it's a relational feature of the information, and it's a thing that remains constant over a transformation. And that transformation could be you moving, or it could be the object moving, or changing light intensity, that kind of thing. I always think about it. I have this weird example from early on in the blog about right-angled triangles. So you know how you can have a right-angled triangle of sort of any size? You can make it bigger or smaller, but all right-angled triangles, there's a relation that remains invariant over that size transformation, and that relation is the Pythagoras theorem, right? And so there's an invariant there, and it's only invariant over these transformations because it's a relation. The specific numbers, the lengths, and all that sort of stuff, that's all can change as wildly as you want. But if it's going to stay a right-angled triangle, that has to remain invariant. And, in theory, if you built an artificial system that could directly detect Pythagoras theorem, then it would be a right-angled triangle perceiver, And the idea is that we do that just with more behaviorally relevant variables.
Next up, degeneracy.
Oh, degeneracy. That's fun. So this is an idea that's cropping up kind of all over the place, and it looking like being sort of the rule rather than the exception. And again, it gets back to the idea of having more than one way of achieving a given function. And this is quite nice, actually, because if you're trying to achieve a function, it's a weird term for it, degeneracy, at one level, because it's actually it's the strength of a system. If you've got more than one way to do something, it means two things. First of all, if you try and do it one way and it doesn't work, you've got something you can fall back on, so that gives you flexibility. And second of all, it also points to the idea that there might not be any such thing as the single right way to do something, which I know that's a topic that comes up a lot with a lot of your other guests and a lot of the sort of the sports literature about. You're trying to train people. Well, what do you train them on? It might not be the case that there's any right way to do it, but what you want is to be able to have sort of experience of some of that variability in order to be able to switch around as you need to. And it shows up all over the place. It shows up in nervous systems. So my favorite example on the blog is that there's, in the gut of the lobster, there's a particular rhythm that has to happen in the stomach to move the food along, and it's really important that this works. And it turns out that given the way the gut is wired up in the lobster, there's something like 450,000 different ways of wiring up a lobster gut and still having it work properly. And that's degeneracy. And that's really, that just goes to show how important it is not to lose access to that motion, right? So nervous systems do it. Action systems seem to do it. Yeah, people are really starting to take it seriously now.
Yeah, I haven't heard it much, you're right, till recently. I guess last one, specification.
Specification, right. So this is a real sticking point for a lot of people. In ecological terms, or in ecological psychology terms, Specification is the idea that, remember I mentioned a minute ago that Jeff kept going on about you've got the world and you've got information, and those two things are not the same thing. So the world, we talked about describing the world in terms of its dynamical characteristics, and that's the level of analysis. So it turns out if you look at information variables, so if you look at sort of the structure that comes off that dynamical world and gets projected into the light, if you look at that, it turns out that it gets projected into what we call kinematic patterns, and that means you get variables like position, velocity, so any change of position, etc., and time, but no mass. So the optic array, for example, you don't need mass units to describe any of its activity, whereas you need mass units to describe the forces that are creating that change out in the world. So the problem, so the specification is you want to be able to perceive the dynamics of the world. All you've got access to is this kinematically changing pattern in the optic array, for example. How does that work, right? They're not the same thing. So how do you use one to get to the other? And so the big argument in the ecological approach, the whole idea is, okay, they're not the same thing, but they stand in what's referred to as a one-to-one mapping, and that specification. The idea is that a given dynamical event out in the world only produces certain information variables. And those certain information variables only show up when that dynamical property is present. And the idea is that they trade out one-to-one, and that means you can use the information to stand in for the world and have access to the world. So it's a very important concept in ecological psychology. It's the idea of sort of the directness of perception, although that's a slightly complicated term. It makes people think there's nothing complicated going on, whereas there is. But specification becomes important because it's the way in which you get to use ecological information variables as if they were the world and have it work. Without specification, you'd never be able to rely, because you'd go, well, I'm picking this thing up, and it mostly refers as property being present, but sometimes and then you're in the world of having to make guesses and do inference, and then you're off to this is why cognitive psychology kicked off, and the things that it does is because it thinks there's no such thing as specification. It doesn't think you can get it. And there's a slightly complicated, slightly philosophical, detailed argument in the ecological approach that kind of walks through how you get it, and it's just because the information is created by the laws of physics, right? And you rely on that, and it turns out to be very useful and important. And then, that specification, that one-to-one mapping between information and world. And because that exists, that means that using the information to stand in for the world works, and then that's why we do so well when we interact with the world.
Yeah, and I think that kind of leads me nicely into the next thing I wanted to ask you about, kind of your views on what ecological psychology has achieved and kind of where it's going. And when I started out and started reading it early on in history, this idea of specifying variables, we had some really strong ones. We had tau and the focus of expansion. And the idea is that we were going to come up with this huge laundry list of them for every other thing, but it never quite seemed to follow that path, did it? So what are your kind of thoughts on how far we've come with this?
Yeah, I agree entirely with that. And it's one of the big frustrations being a loudmouthed advocate of the ecological approach. I do have people very rightly shoving this back in my face a little bit, and that's fair. So tau is information for time to contact. Everybody was super excited about that until it turned out that it was actually all much more complicated than that. This is one of the things I would like the field to really knuckle down and get more serious about. There's a lot of work that comes out talking about the affordances of things, and that's fine. You have to do affordances first, but you also then have to do information second, or else you've missed the whole point of the analysis, right? Gibson's got this quote, and he's like, affordances are real. Of course they are. But the question is, they're only if you can perceive them. You have to have a story about the information. And I don't think the ecological approach has. We've written checks about information, but we haven't quite got the data to help those checks in some cases. That said, though, there are small pockets of good work. So, there's all the Bill Byrne, for example, has been doing flow stuff and getting serious about information variables for navigation steering for a long time. There's obviously the stuff he and Brett did in navigation and steering, and then the competing model with Wilkie and Wan, independent of they're having arguments about which information variable gets used under which circumstances, but at least they're tackling information, right? They're really trying to get into that argument. So that work is pretty good in terms of taking this seriously. The stuff that I do, so I kind of pack around in the kiddie pot information. I do this task coordinated movement, and that was my PhD, was looking at the information that people use to coordinate the movement of, say, wiggling limbs, the original Scott Kelso task. And that again comes from Jeff. Jeff has been working on this for a long time, and I are continuing to work on it. And it's this little test bed for doing information is very simple. But you know what? Like, one of the papers in my PhD was about doing the dynamical analysis and figuring out what information variables rhythmic movement created, and then figuring out empirically which ones people were using. Like, all I'm doing is rhythmically moving dots on a screen. It was some of the hardest work I've ever done trying to get the information right and do the experiments properly. And that got ground through the mill at Perception Psychophysics. And we had a reviewer who worked really hard actually with us, and the paper that came out was much better. But part of the problem is that we need to take information more seriously. And a very real problem of that is that it's really, really hard. And as soon as you get into complicated, interesting information variables and interesting, the maths gets tricky. So, if there's any computer scientists or engineers or mathematicians who want to have some fun and play some interesting geometry, come talk to people like us because we need the help, So, yeah, I think I agree with you that there's been a lot of that started out early on and looked really promising, and a lot of it's kind of fallen through, had some problems, but I think that there are some pockets of real progress going on. And then Mike was like, I don't care about coordinated movement really, like not as a task, but I just use it to kind of develop the intuitions and working there. What I'm trying to do is I'm trying to build methods and build analysis techniques and build ways of thinking, ways of talking about the problem, so that when I get into something like growing, I've now got a whole sort of repertoire of experimental techniques and ways of talking that I can try and apply to see if I can figure out what's going on and how perceiving target location, for example.
Yeah, no, I totally agree. I don't think that the idea is flawed. It's right. It's just, I think it's way harder than people, people really in it, I'm sure, anticipated it. But from the outside, Tau, it's such a simple, elegant solution. So it's focused on they're all going to be like that. And then there's other thing we said at the start. People just have not, compared to cognitive psychology, where there's like 40 million papers on the Stroop effect, we just haven't. Ecological psychologists tend to spread themselves out a lot, so there's not that much digging in on the similar tasks. And so I think you're right. It's going to take time and a lot of effort, but I think it's still a good approach.
Yeah, what's funny. So, a lot of stuff is tricky. You need specialist equipment to kind of pull some of this off. Like, you need a decent sized lab. You sometimes need motion capture gear. You need computer programming and all that sort of stuff. And it's not impossible, but it's difficult to set up a lab like that, and there's a group setting itself up to kind of develop a ecological psychology replication project, try and pick the key findings in eco so I can try and replicate them sort of in line with what's going on in ecology more generally. And I'm thinking about it, and I keep thinking, you could do that. Yeah, but you need some gannets. I was like, you could do that. No, but you'd need a motion capture lab with so it's, I agree. Like, we just end up off in these pockets and these little individual tasks, and it's to get that momentum going.
Yeah, no, I've had the same kind of thoughts too. I'll let you borrow my batting simulation if you really want to try to replicate that. So I guess the last question I have for you, Andrew, is, can you tell us, a little bit about what you're working on now and what's kind of next on your plate?
Yeah. So I think I mentioned, I'm on a research sabbatical semester, so thanks very much to the faculty for helping that. And the idea is that I'm finally in a position now throwing papers out, got a bunch of experiment ideas and related to just throwing in general and also the prehistoric stuff. I finally kind of got enough that it's worth sitting and trying to turn it into account. And so even if we don't get funding, I'll still have a big pile of experiments that need to get run at this point so we can do them in various ways. So I've got this sabbatical now to kind of pull all that together. So a few months, it's my big focus. A book chapter that I'm writing with just to get this task dynamics information stuff out into a handbook and then focus on the grant. And we've got learning data, throwing tasks that I collected ages ago and I need to write up because, as we were talking about, the next place to go playing with is that's where some of the real meat is for these kinds of tasks. We've set it up. So my big kind of focus is getting the throwing up and running, and I want to get it up and running and properly funded and supported with staff and all that sort of stuff. So if we can do that, that would be cool. We've got more coordinated rhythmic stuff, so more sort of empirical work looking at the information of things and just building those techniques, looking at transfer of learning. And I've got a PhD student working on learning and transfer of learning. We're going to do a little TDCS work to see if we can do TDCS in the context of a well understood. So that's the current stimulation, the brain stimulation that it's sort of main selling point is people can get affects learning rates and can enhance learning rates. And so just going to try and get into it and coordinated rhythmic movement is a well understood task that we know about and that we know how it works. We can poke it in a bunch of different ways, and so we're going to look at that. And then I collaborate with Sabrina Golonka, and she and I write the blog together and do the Twitter and all that sort of stuff. And we collaborate on sort of the big theory stuff. Her interest more sort of in things like language and some of those really complicated things psychology hasn't wanted to ever touch. So her big goal has been, now that the ecological approach is a fairly sensible to try and do, she's now pushing to try and figure out how to do things like language ecologically. We've got 2 papers that we're working on at the moment. A fairly big one that we've put out as a preprint and editing now, and another one we'd actually like somewhere like BBS and get a lot of feedback on big theory paper where we're trying to tie it all together. And the big goal for us is we're trying to develop a vocabulary, like a framework and a set of terms that people can use to figure out ways to study some of these problems ecologically if you want to get into it, right? We're trying to just lay out the tools the ecological approach has available to, right? It has some things and not other things. You get mental representations, but you do get information, so that has consequences. And we're just trying to lay it out in a way that provides a way for people to talk about these problems, and just see then, because we'd quite like some other people to be some of this too, because we can't at all. But that's another big project that's been going on for a little while, and we'll to have those out by the end of the year. So yeah, that's the throwing's the big empirical focus, and these theory papers on that side of things. We're trying to get this stuff done.
Well, that's great. I think that's all the questions I have for you, Andrew. Thanks for taking some time to talk with me.
My pleasure. Thanks for having me.
Thanks again for the great discussion, Andrew. I look forward to seeing how you put your throwing model and paradigm to use in the future, and will continue to look forward to reading your blog posts. You can find more information about Andrew from the links in the show notes. He's definitely a must-follow on Twitter. Coming soon on the Perception and Action podcast, stop calling them driving accidents. This is Rob Gray from ASU. Cheers for now.